In this video, we're going to finish our discussion of section 13.2, all about the integration of vector functions. Last video was about differentiation. As I said in that video, we're mostly going to use this as an excuse to review integration skills ahead of chapter 14, where things will get a little more complicated. But the big idea, again, is it works the way you would think. So the integral of a vector function r of t dt is going to be the integral of the f component, with respect to t, the integral of the j component, and the integral of the h component. Okay? And so we're going to have all the same integration properties we used to have, and we're just going to walk through some examples. So for instance, if I have an integral from 0 to 1 of t in the I component plus t squared in the j component plus t cubed in the k component, what is that going to do? We're going to integrate each of these functions, which should not be a problem as long as you remember integration. So, what does that mean? Add 1 to the power, multiply by the reciprocal in the I component, in the j component, and in the k component. So here's the integral of the twisted cubic, and we're going to evaluate that from t equals 0 to t equals 1. We notice that when we plug in 0, we get 0, 0, 0, so that's not really interesting. Instead, I'm going to get 1/2 I plus 1/3 j plus 1/4 k. And that's the integral of that vector valued function. You might wonder what this represents. You could say it's the displacement. If this was a velocity function, this is representing the displacement vector. Okay, we're not going to get too hung up on that. It's all the same as it was before. So if we're traveling on the space curve, what this integral could represent, if we were integrating the velocity on that space curve, we would get the displacement of the space curve. Okay? In general, we want to know how to do anti-differentiation for lots of reasons that you're familiar with from Calculus 1. So what would an indefinite integral look like? So example 2. If r of t was 2 cosine t in the I plus sine t in the j plus 2t in the k, what would the integral of RT look like? So we could just go through and anti-differentiate each of these components, but I want to say one big caveat. So we'd obviously have an I, a negative cosine for the integral of sine in the j, and a 2t squared would turn into, a 2t would turn into a t squared in the k component. You might remember that in 2D, the integral of x was x squared, 1/2 x squared plus a c, where that c was some constant. Well, now we need to add a vector valued c. Vector. It needs to be a vector. Why? Because each of the indefinite integrals we did would have its own c. We'd have maybe a c1 in the I direction plus some c2 in the j direction plus a c3 in the k direction. And so what we're doing is we're grouping each of these c components as their own vector at the end. And that'll make certain things tricky, but honestly, it shouldn't be too bad. It'll make things a little trickier when we go to solve for initial conditions and stuff like that. But in general, just know that if you integrated a vector valued function, the constant of integration needs to be a vector constant. Okay? So like I said, these are not the big concerns for me personally. For you guys, I would say the bigger concern is, do you remember how to integrate something like this? T cosine t in the I direction plus t sine t squared in the j direction plus, minus t e to the t squared in the k direction. So for answer keys, I usually am not going to write it this way. But because I'm trying to show you all the different integration techniques you may or may not remember from previous years, let's go through it. This integral involves 3 separate integrals. First, in the I component, how do you integrate something like t cosine t? Well, I don't see any way of doing a u-substitution or a hook-on type strategy where I have an easy chain rule between the derivative of the inside and what's a coefficient now. So I'm going to use the product rule for integration. Might be how you might remember it. It's integration by parts, which is liate, however you want to remember it. U is going to be t. We want to make sure we find du. And then I want to have dv as the other part. So I'm picking the algebraic part to be u. dv is all of the rest of the inside of the integral. The derivative of u would be dt. And v would be the integral here, which is sine t. And so what we have is uv, right? So it's the integral of u dv is supposed to be uv minus the integral of v du. And that came from the integration of the product rule. That's why it's like the reverse product rule. If this does not look familiar, I urge you to watch a video on it, either my video or any other math YouTuber's video, to refresh these skills. We're going to use integration by parts a lot in this class. So, replacing everything in that rule, we have t sine t minus the integral of v du, sine t dt. And so that would be t sine t plus cosine t. And again, this was an indefinite integral, so plus c1, because it was the first component. Okay? You could say c there. I'm not really interested in writing it that way, but that's what's going on in the I direction. In the j direction, this is what I'm talking about when I talk about reverse chain rule or a u-substitution, if it makes it easier for you. What I'm thinking is, okay, there's a t squared here and a t there. So this can come out of the chain rule. The derivative of the inside would have been 2t, and so I can compensate for that with a 1/2 on the outside. You could just do u equals t squared, du equals 2t, and solve it that way. You could solve it that way if u substitution seems easier for you. But in general, I'm going to say, well, let's write it like this. I'm going to multiply the outside by 1/2, the inside by 2, so then I can clearly see the chain rule situation I have. I don't need the product rule here because I'm saying I have the derivative of the inside is right here, ready to be hooked off. The opposite of hooking it on, the opposite of using the chain rule. So I'm getting 1/2, and then the integral, the antiderivative of sine is negative cosine t squared plus c2. Check your work. What's the derivative of cosine? Negative cosine. That would be positive sine. Take the derivative of the inside would be a 2t. And I would multiply with that negative 1/2, that 1/2 to get back to 1t. Probably going to write it like this exclusively, especially because you can do it in your head. One more. I'm going to try to integrate it with the sign here just to make everything crystal clear. And I'll say this is a lot like the one from above. So if what I just did didn't make much sense, or if it seemed to refresh you, I would try this out. Okay. The only difference is I'd multiply maybe by a negative 1/2, where I'd pull out the negative so I could write it like this. And again, here's the relationship. T squared, 2t. Derivative, original. Negative 1/2 e to the t squared plus a third constant. So if I put it all together, what we have is this thing equals t sine t plus cosine t in the I. Could you put a C1 in there? Sure. If that makes it easier for you, put the C1 in there. You're probably not going to see my answers with that. It's not how most books would write it. Plus minus 1/2 cosine t squared j minus 1/2 e to the t squared k plus all of those other constants as a vector. A few more things to go over, a few more different rules to remember. One over 1 plus t squared, I component. T over 1 plus 2t squared, j component. Minus, let's do minus 1 over square root 1 minus t squared in the k component. Do some of these look familiar? Try it out. See if you remember which rule's which. Here I go. 3, 2, 1. If I see 1 plus t squared in the bottom and a 1 on top, that situation is inverse tan or arctan. However you want to write it. I'm going to write it as tan inverse t. Over here, we should notice that there's a t on the top. Well, if I thought about the derivative of the bottom, like a u-substitution, if u was the entire bottom, the derivative would be 4t. And so I want a 4t on the top. It's that kind of situation where we're talking about u prime over u would be 1/4 natural log absolute value 1 plus 2t squared. I'll show my work a little more clearly over here. I'm thinking it's a log rule because I can see the derivative of the bottom is going to give me a t, which is what I have on the top. So what I'm doing is I'm multiplying the top by 4 and the outside by 1/4. That's the derivative of the bottom. Reverse chain rule would get us to the blue in the j direction. This last component here is a derivative rule you used to have memorized, maybe you don't anymore. Arc sine, or I guess sine inverse to keep it consistent, of t in the k component. And like I've been saying, it's okay if you don't remember all of these right now. You should refresh yourself, and you should be able to do all these things after trying them out again. Okay. As promised, what about solving for the constants of integration? What about solving for the constants of integration? So example, they tell you r prime is 2i plus 4tj minus 6t squared in the k direction. And they tell you that you know the initial condition is j plus k. So I gave you an easy one here. Easy, quote unquote, depends on how fresh you're feeling. Do you remember the steps? What do we need to do first? The first thing you need to find me is r of t. Specifically, we're going to integrate r prime. You don't have to write this, but you do have to remember how to do it. Go ahead. Get me the antiderivative of this as a vector function. 3, 2, 1. You should have gotten 2t in the I direction, 2t squared in the j direction, minus 2t cubed in the k direction, plus c. Did you forget that? That c is the most important spot. Full stop. Okay, what's next? Evaluate at 0 the value they give you. Well, I would get 0i plus 0j minus 0k plus c, and that's supposed to be equal to j plus k. So j plus k equals c. So when I go to write it all, I can substitute this value in for the c there. I'm just going to show you what this looks like. One way to write it would be like this. Plus j plus k. But we usually don't write it like that, right? We usually want to group the j's and the k's together. So you're supposed to 2t in the I, there was nothing to add in the I direction, plus you could write it as like 1 plus 2t squared in the j direction. Make sure you're using your parentheses. You could also write it as 2t squared plus 1. The order there doesn't matter. And then here again, you want to make sure you're using 1 minus 2t cubed or negative 2t cubed plus 1 in the k. I really encourage you to change it to a plus and put the positive number in first if possible. Notice some students will end up writing like this, and that's wrong. Those are not the same thing, right? You'd either have to make this guy negative also, or you'd have to do something more complicated. I think this is the nicest way to write it. I want to give you one more problem to review this, make it a little more complicated, a little more fun. Let's go back 2 steps now. This should model the progression you had when you first learned integration. It can feel overwhelming to some students because you're doing it all at once. Like all of a sudden we're expecting you to remember the integration by parts, we're expecting you to remember all these different reverse chain rules, u-substitution, solving for constant integration. It's really not that bad. I think you guys can get it. You just need to shake off the dust. Secant squared t in the j. And we'll keep it nice and simple. E to the t in the k. So that's r double prime. They'll tell you an initial condition for r prime is, let's say it's I plus k, and r, the initial position, so to speak, would be 2i plus j minus k. And they want you to go all the way back to r. They want you to go all the way back to r. So how do we do that? First step, find me r prime. Just integrate each of these components. We're trying to integrate each of these components and find me r prime. You don't have to write that integral every time. You should know what we're doing is an integral. Pause the video, really try to write this down. Try to get me the new functions here. You might have to go look up secant squared, but it's a derivative you're supposed to know. Hint. 3, 2, 1. Add 1 to the power, multiply by the reciprocal, I. Secant squared is a known derivative. It's the derivative of tan in the j direction. E, the easiest one, in the k direction, plus, now I'm going to write that as k, constant 1. Okay, it's technically we're going to have two constants integration. We're going to integrate twice. We got to watch out for that. So, r prime evaluated at 0, we'd get I tangent of 0i plus 0j plus k, 1k. Careful, careful. That's really important here, folks. If you have to readjust, try again. So I plus k equals k plus C1. So what does that mean? That means C1 is actually I hat. And it means that R prime, that's going to get added to the I hat stuff. I'm not trying to lose anybody. I'm just going to put it all in here. So that's 2/3 t to the 3 over 2 plus 1, the I direction. So you don't want to just start assuming you're going to get another 1 in the k direction. It's not how initial vectors work. It's not how initial conditions worked in AP Calc or Calc 1. We just have this function. Okay? Take a second. Make sure you understand. Why did we go from having this to this? It's because after all of the initial vector stuff, we do have initial in the I. In order to start off with a velocity in I plus j, we had to say it was this function in order to have the right initial condition. Now we're going to go for r. This is just a second integral. Can you integrate this? You might have to look up tan. It involves a natural log. 3, 2, 1. Add 1 to the power is t to the 5 halves. Multiply with the reciprocal, that's 2/5. So we're talking about 4/15 plus t, integral of 1 in the I direction, minus natural log, absolute value, cosine t, because we're talking about the integral of sine over cosine. And so it's a log substitution. You're really supposed to remember that rule. If you have to look up that rule, it's probably not the worst thing in the world. Plus e to the t in the k direction, plus another constant integration. Now we plug in 0 again. Plug in our new initial condition. I'm getting 0 in the I direction, 0 in the j direction, and yet again, 1 in the k direction, plus C2. So that means 2i plus j minus k is meant to equal k plus C2. Well, that means that C2, as a vector, must have been 2i plus j minus 2k. And so if I'm going to try to recombine everything now, it must be the case that r of t, I'll write it without it grouped immediately, so we can see it. 4/15 t to the 5 halves plus t minus natural log absolute value cosine t in the j plus e to the t in the k plus 2i plus j minus 2k. And all we're doing here is nothing more than combining like terms. A skill you learned a long time ago. You got this. So the I stuff gets combined. 4/15 t to the 5 halves plus t plus 2, the I direction. The j stuff gets combined. Careful with the sign. I recommend writing it like 1 minus natural log cosine t in the j direction plus e to the t minus 2 in the k direction. And that's all it takes. Just hard work, focus, and you can do this. You can remember how to integrate. I believe in you. Thanks for watching. I hope you refreshed. I hope you feel refreshed. Do the homework for 13.2, and I'll see you in the next video. Thanks. Bye.